All right, let's try this example. We're going to find the local maximum and minimum values of this function f of x equal to 1/3 x cubed minus 2x squared plus 3x plus 1. We've looked at this function before, I think when we talked about intervals of increase, decrease, and we're going to try it again here. And maybe some of the details here we'll cover, but maybe not in as much detail as we did in those intervals of increase, decrease section. All right, so how do we find where the local maxes and mins occur? First step, we want to find the critical numbers. So that means calculate the derivative. Derivative of this function is x squared minus 4x plus 3. And then we want to find the critical numbers. So that's where either the derivative is 0 or where the derivative is undefined. So we want to try to simplify this derivative. And a lot of times the way we do that is with factoring. So we did this, like I said, back in those intervals of increase, decrease lesson. So we'll review it here, but we're kind of go through a little bit quicker. So we factor this into x minus 1 times x plus 3. And why it's helpful to have this factored is because then locating where the derivative is 0 just comes down to setting each of these factors equal to 0. So from this first factor right here, we get x equal to 1. And from the second factor here, we get x equal to 3. So that's where our derivative is 0. X equals 1 and x equals 3. Derivative undefined, this is a polynomial, so it's always defined. So there's no contribution here where our derivative is undefined. All right. So these are, I guess, possible critical numbers. There is one more thing to check. For our actual critical numbers, they need to be in the domain of our function. And our function here is also a polynomial, so yeah, these are in the domain of our original function. You can plug 1 in. There's no division by 0. There's no natural logs where we might run into an issue. No square roots where we might have a negative under the square root, kind of the usual things. Same thing with 3. We could plug 3 into this and get something meaningful out. So both of these numbers are in the domain. So our critical numbers are x equals 1 and x equals 3. And we just note both in the domain of our original function f. So that's just something to keep in mind. All right. So we've identified our critical numbers. So these are the two places on our graph. Out of all the different x values on this function, there's only two places where we might have a max or a min. So we've located those. Now it comes down to testing it. We want to test them. Are we going to have a max, a min, or neither at x equals 1 or x equals 3? So let's try the first derivative test. We have options. We have first derivative test we could use, or we have the second derivative test we can use. We'll do both for this one, but normally you'd only do one. All right, so we found our critical numbers. We would draw in our number line. We would plot x equals 1, x equals 3. We'd plot our critical numbers. This is just like we would be doing for intervals of increase, decrease. This really splits up our number line then into 3 intervals. So minus infinity to 1, 1 to 3, and then 3 to infinity. And then we'd be looking at the sign of f prime on each of those intervals and see what that tells us about our original function f. And so the way we fill in the sign chart is with test numbers. So for this first interval, maybe 0. Use test number 0. Plug 0 into our derivative. We get 0 minus 1 is negative. 0 minus 3 is also negative. So it's a negative times a negative, positive. When we did this before, we actually listed out the different factors. So that's probably how you'd want to do it, just so you don't make a mistake. Right now, we're just kind of reviewing over really what we found in a previous example. What about this middle interval? We could use a test number, say t equals 2. Go up to our derivative, plug 2 in. We get 2 minus 1 is positive. 2 minus 3 is negative. So positive times a negative is negative. And then we go to our last interval, 3 to infinity. Pick a test number somewhere in there, 4, 5, anything works. Let's use 4. go up to our derivative, plug 4 in, we get 4 minus 1, positive, 4 minus 3, positive, positive times positive, positive. So, normally we'd have a little bit more detail here on our sign chart. We'd actually list out the factors and kind of go through all that. And then when f prime is positive, that means our original function is increasing. And then when it's negative, that means our original function is decreasing. And so what we're seeing here is at x equals 1, we're seeing a sign change. We're going from positive to negative. And at x equals 3, we're seeing a sign change. We're going from negative to positive. So something actually is happening at both of these places. And to really kind of help us remember, what does the first derivative test say? Let's kind of sketch out roughly what our graph is going to look like. So it's increasing. Then at x equals 1, it starts decreasing. And then at x equals 3, it starts increasing again. So really rough sketch. Probably could make this a little more rounded, but we're just trying to remember what the derivative test tells us. And if we're going from increasing to decreasing, we have a local max. And if we're going from decreasing to increasing, if we switch signs from minus to positive, we have a local min. And so that's what we're seeing. At x equals 1, we have a local min, or a max, and at x equals 3, we have a local min. So let's write that down. We have a local max at x equals 1, and we have a local min at x equals 3. Now, sometimes we're interested in, well, what is the max value, or what is the min value? So if we wanted to actually find what is the local max value, we've identified where it happens at x equals 1. So to find the value, we would take 1, our critical number 1, plug it into the original function. And when we do that, we end up with 7/3 here. Same thing for the max value, or the min value here at x equals 3. Sometimes we're actually interested in, well, what is the value of our function there? And so if we see wording or phrasing for the max value or the min value, we want to know the location, the x value, or the x location here. But if we're interested in the min value, well, that's where we go take our critical number and we plug it into the original function. And so if we were to plug 3 into this function, we're seeing a local min value of 1. Yeah. All right. So that would be it. Given a function, first find the critical numbers. So calculate the derivative, figure out where the derivative is 0, where it's undefined. And then once you've identified that both of these numbers are actually in the domain of our function, then we'd go through and classify them with a sign chart if we wanted to use the first derivative test. Now let's suppose that we wanted to instead use the second derivative test. So you don't normally do both of these in the same problem. You do one or the other. Well, let's see what we get from the second derivative test. So if we look, here's our first derivative. Let's differentiate that to get our second derivative. So derivative of x squared is 2x, and then derivative of minus 4x is, what is that, minus 4. So our second derivative here is 2x minus 4. And what we would do then is we would take each of our critical numbers, and so x equals 1 and x equals 3, and we would just plug them into this second derivative. So if I take x equals 1, plug it in here, what do I get? I get 2 minus 4. So I get negative 2. The number here really isn't too important. It's just the sign that's interesting. And so this is negative. And to help remember what the second derivative test says, draw in the shape. It's concave down. And so drawing in the shape just really kind of helps remind us that, yeah, concave down shape, we're going to have a local max here by the second derivative test. And that's precisely what we found from the first derivative test. We have a local max at x equals 1, and that's what we're seeing here with our second derivative. Now, if we were to do the plug 3 into our second derivative, what do we get? We get 6 minus 4, which is positive 2. We don't really care about the number, just the sign of the number. So this is positive. And what does positive mean? Concave up. So draw in the concave up shape. This is what it's going to look like. And what does that look like we just drew? If that's our curve, it looks like we're drawing in a low point. And that's exactly what the second derivative test tells us. If the second derivative is positive, then we have a local min. And that also agrees with what we found from the first derivative test. So this example, we're kind of showing everything. Normally, you don't do both tests. You do one and not the other. Sometimes if you do the second derivative test and you get it's inconclusive, then you gotta have to go back and do the first derivative test. But normally, if things are not inconclusive, you're only doing one of these. All right, so a nice little example. We'll try a few more just to get practice with this.